welcome to the deep dive. You're keen to understand the backbone of modern tech, and today we're plunging right into the fascinating world of semiconductor manufacturing, specifically in Taiwan.
Yeah, absolutely.
You've shared some great resources, transcripts from Taiwan Plus Docs, Inside Micron Taiwan Semiconductor Factory, and the TSMC Museum of Innovation's factory tour.
Mm-hmm.
Get ready for a journey into these incredibly intricate processes that, well, basically make our digital lives possible.
And what these sources really highlight is Taiwan's, well, undeniable leadership in this really crucial global industry. I mean, we're talking about a nation that commands nearly 70% of the world's semiconductor foundry services.
70%.
Yeah, and a staggering, like over 90% in the most advanced fabrication. Yeah. Plus a huge presence in assembly and testing. And it's not spread out everywhere, it's largely concentrated within three main science and tech parks there.
Absolutely. And leading the charge are giants like Micron and TSMC. Micron, as we learned, has set up this massive manufacturing hub in Taiwan. They make something like 65% of their DRAM there.
That's right.
Which is like over 10% of the entire worldwide market.
Yeah.
They're really pushing the boundaries on memory tech.
Definitely. And then you have TSMC, the undisputed king of leading-edge logic products. They basically pioneered the whole dedicated IC manufacturing service model.
Oh, the foundry model.
Exactly. And now they produce, get this, over 10,000 different types of high-yield, high-quality integrated circuits every year. You find their chips in pretty much everything.
Your phone, your laptop, sophisticated AI systems.
Yeah.
Everywhere.
So the mission today, based on, your interest, is to really get under the hood of these Taiwanese mega factories. We want to explore the sheer scale, the relentless innovation, and ultimately give you a much clearer picture of the tech that underpins, well, almost everything now.
Okay, let's dive right in then. One of the first things that just jumps out from both sources is this almost unbelievable obsession with cleanliness. Micron even hints their plant might be the world's cleanest.
And that's probably not far off. This isn't just tidiness, right? It's fundamental. Think about the scale transistors now are, what, tens of thousands of times smaller than a human hair.
Incredible.
At that level, even one microscopic dust particle can be, well, catastrophic. Causes defects, ruins the yield. It's like trying to do brain surgery in a sandstorm, basically.
The entry procedures sound totally sci-fi.
Yeah.
Both Micron and TSMC's Jinyuan factory, they have these super rigorous protocols. You're talking metal detectors, ID checks, and then this whole transformation into, like, someone ready for an alien planet. Micron calls it a bunny suit.
Right.
TSMC calls it dust-free clothing. But it's the same deal. Head-to-toe covering, gloves, masks.
And the air shower. Can't forget that.
Oh, the air shower, yeah. That final blast to dislodge anything left. It's all about creating this fortress against contamination. Micron even said their production line is 100 times cleaner than a hospital operating room.
Wow. That really puts it in perspective, doesn't it?
It does.
And at the very, very core of all this complexity is, well, a surprisingly simple element, silicon. It's the foundation. And its key property is that it's a semiconductor.
Meaning it sometimes conducts electricity, sometimes doesn't.
Exactly. Depends on the voltage you apply. Think of it like a tiny gate you can open or close for electrical current.
Right. And Micron explained that the workhorse component here is the transistor. These tiny switches representing the zeros and ones of binary code.
Yeah, the fundamental building blocks.
It sounds basic, but like they said, a modern chip is just this vast, intricate network of billions of these switches. Like an orchestra,
An orchestra with hundreds of billions of musicians, maybe, in something like a new smartphone chip.
Hundreds of billions.
It's almost impossible to grasp. All these microscopic on-off switches working together perfectly. And as both sources stress, the more transistors you pack in, the more complex the calculations, the more powerful the device.
Faster communications, better AI, medical advances, military tech.
Exactly. They're truly the building blocks. Yeah. Billions of switches, smaller than you can see, all on one tiny piece of silicon. That's the power and, I guess, the fragility, too.
So how do we get from that silicon base to these chips packed with billions of transistors? Let's walk through the manufacturing process. First up, as Micron described, is design.
Right, the architecture.
It's this huge undertaking. They compared it to designing a skyscraper, figuring out the blueprint where everything connects.
Yeah, it's a good analogy. And TSMC added that this design phase uses really sophisticated computer-aided design, CAD systems. Engineers map out the detailed circuit layouts for every single layer of the chip.
Every layer. Wow.
Yeah, and these digital designs then get transferred using electronics or lasers onto a series of glass masks. Each mask is like a stencil for one specific layer.
Okay.
As TSMC noted, the more complex the chip, the more layers, and so the more masks you need.
Makes sense.
Yep.
Okay, so you have the designs on the masks. Next is prepping the actual silicon wafers. TSMC gave a good overview here.
Starts with polysilicon material.
They heat it super hot until it melts, then carefully draw it out into these long, cylindrical ingots, pure silicon rods.
Like pulling taffy, but way more precise and hot.
Yeah. Then they grind them perfectly round and slice them into thin discs, those flawless, smooth wafers, usually 12 inches across, like Micron mentioned.
And TSMC also pointed out that during this stage, they add specific elements called dopants.
The impurities.
Exactly. Carefully adding these modifies the silicon's conductivity, its electrical properties. It's like adding a tiny pinch of salt to water, changing how it behaves.
Gotcha. So you have these perfect doped wafers. Now the layering starts, right? Thin film deposition.
Correct. A really critical step. Both Micron, talking about their furnace tube area, and TSMC, with their high-temperature thin film growth area, describe this. It's about forming incredibly thin layers, metals, insulators, other semiconductors onto the wafer surface.
In super controlled environments.
Absolutely. Temperature, gas flow, everything managed precisely. TSMC mentioned chemical vapor deposition, CVD. That's a key technique.
PD.
Yeah, it uses controlled chemical reactions in a gas state to deposit solid materials as ultra-thin films. Think of it like incredibly precise spray painting, but at a molecular level, building up layer by tiny layer.
Okay, then comes a step, both sources, called pivotal photolithography, patterning.
Yes. Micron's reticle area, TSMC's photolithography area. Micron had that great comparison to old darkroom photo printing.
Right, but inside a $100 million machine.
Exactly, with insane accuracy. Because remember, transistors are 10,000 times smaller than a hair. This is how they do it.
So how does that work exactly?
Well, first, you apply a thin, even layer of a UV-sensitive liquid called photoresist onto the spinning wafer. Then, you align one of those detailed masks precisely above it.
Like the stencil.
Right. Shine UV light through the mask. It optically prints the circuit design onto the photoresist. The exposed parts solidify, the unexposed parts stay soluble.
And get washed away.
Precisely, leaving behind this patterned layer of photoresist that mirrors the mask's design. And you repeat this over and over, different masks for each layer, building up the 3D structure.
Wow, okay, so after patterning comes etching and ion implantation. Micron and TSMC both have dedicated areas for this.
Yep. Etching is basically removing the unwanted material, revealing the patterns left by the photoresist, like a sculptor chiseling away stone.
Okay, and ion implantation, that sounds intense.
It is pretty cool. You accelerate ions, charged atoms, and fire them into specific areas of the wafer with incredible precision to control the electrical conductivity of the silicon in just the right spots, at just the right concentrations and depths. This is how you actually create the transistors, by tuning the silicon's properties in targeted regions, like adding specific ingredients to different parts of a cake.
Fascinating. So now you have the transistors built in the silicon. How do you connect them all?
That's metallization and interconnection. Both sources mentioned depositing thin metal layers. Micron specified physical vapor deposition, PVD.
Like the CVD earlier.
Similar idea, different technique for metals. And TSMC added that these metal layers are also patterned, using more photolithography and etching, to create the wiring, the conductive pathways linking billions of transistors.
The chip's internal electrical grid.
Good way to put it. And TSMC also highlighted something called chemical mechanical polishing, or CMP.
Polishing.
Yeah, after each layer is added, CMP makes the wafer surface perfectly flat and smooth. Imagine polishing a gem, but microscopically. This flatness is absolutely crucial for the next lithography step to align perfectly.
The precision is just staggering at every step.
It really is. And what's equally remarkable is the scale and the automation needed to manage it all. Both Micron and TSMC stress this heavily.
Micron's overhead robots, the little buggies.
Yeah. Traveling on rails, moving wafers between hundreds of stations, covering almost 400,000 kilometers a day.
That's like 10 times around the Earth. Every day.
Exactly. And TSMC has their similar automated material handling system, AMHS, essential for efficiency and keeping things clean. Imagine robots covering continental distances daily, just moving stuff smaller than a virus. That's the scale.
And it's not just efficiency, right? It's about minimizing human contact.
Absolutely. Reduces contamination risk drastically. Micron pointed out how things have changed. Used to be manual loading. Now with automation, one technician can oversee way more machines.
Hundreds, maybe?
Potentially. Micron mentioned having around 5,000 equipment units, but a production shift only needs 70 to 90 people.
In a remote control room.
Yeah.
The Starship.
Yeah, that evocative term. It highlights how central data and remote monitoring are now. Micron talked about 50,000 sensors, 250 million control points.
Generating 30 petabytes of data daily.
Mind-boggling amounts. The human role has shifted, from manual labor to knowledge work, analyzing data, optimizing processes, spotting issues before they happen.
Okay, so after all that complex layering and connecting, you have a finished wafer full of chips. Then testing and packaging.
Correct. TSMC mentioned wafer probing, an initial electrical test while they're still on the wafer, checks basic functionality.
Then dicing, cutting them apart.
Yep. Micron said it's surprisingly one of their oldest technologies, using diamond blades to cut the wafer into individual chips, or die.
And then they need to be connected to the outside world, bonding.
Right. Micron described using superfine gold wires to connect the chip to the circuit board pins. But the bare silicon die is fragile.
So it needs protection.
Encapsulation.
Exactly. That familiar black protective casing Micron showed protects against humidity, corrosion, mechanical stress.
Yeah.
Then more final testing. Rigorous testing.
Very. And the qualified chips get laser marked for tracking and shipped out.
It's just an incredible journey for each tiny chip. But, as Micron noted, this progress isn't free. It takes a lot of resources.
Huge amounts of water and electricity, especially as processes get more complex.
Yeah.
And both sources touched on the environmental side. The industry is aware and making efforts. Micron highlighted recycling isopropyl alcohol, reclaiming nearly 80% of their water.
80%? That's impressive.
It is. And those vertical green walls they mentioned, 18,000 square meters to help save energy and create green space, plus using more renewable energy.
Which really brings us back to Taiwan's absolutely crucial role in all this. It's not luck, is it?
Not at all. As both sources emphasize, it's decades of experience, strategic location, a strong manufacturing base, and that unique co-location of TSMC's leading logic and Micron's leading memory.
All in one place.
Right. Limited natural resources, but indispensable to global tech through, as Micron put it, collective effort and lots of smart people.
So wrapping up this deep dive, what's clear is that semiconductor manufacturing in Taiwan is just this extraordinary achievement. It's art and science, precision, ingenuity.
A breathtakingly complex fusion, and its relentless 247 innovation driving human advancement.
Absolutely. So next time you send a text, stream a video. Just take a second to appreciate the journey of those tiny chips inside, the immense effort involved.
Yeah. Which leaves us with a thought to ponder, doesn't it? Looking ahead, with material science constantly advancing, how might future breakthroughs revolutionize these processes even further?
Smaller, more powerful, more efficient chips.
Potentially. What could that mean? Not just for our gadgets, but for the whole technological landscape. Something to think about.